What's up, Warriors? Tonight we're going to talk about sampling. That's how I feel doing videos and talking through that Internet of Things. But you got to do what you got to do. So, take that D3M pledge. I will always drop science with defiance. Now let's get down to this thing called sampling. All right, so first of all, we sample when we want to get some of that funky drummer. No, I'm just kidding. We sample when we cannot or don't want to or don't have the time to know what's going on with the population. So let's think about this. If we could count or take every measurement within a group that we wanted to know about, then we would have no need to sample it. And this is the case in smaller populations like our class, like a sports team, like, I don't know, a small group of people, a fraternity, a sorority that we are interested in and we can get all the information, and that's descriptive statistics. But that's not what we're talking about here. Because we're talking about those larger populations that I often refer to as a type 2 or 3 population where we can't get all the data. We either could, but it would really take a long time, like all the sophomores at York College, information that the registrar doesn't have readily accessible, or all of the sophomores in the world. That would be just downright impossible to find out. So, back into the need for sampling. Of course, all the fundamentals with samples still apply. If I run out and get a group of friends or a group of students that I know that are sophomores, and I find out data about them, and then I try to project that across all sophomores, then I run into the problem of convenience bias. So what I've got to do is, like we've always talked about, create an equal opportunity that I can get that information. So I might take every fourth person that I encounter, or I might make it so my survey is random and anonymous, or whatever way I collect my data. But I always got to remember that I've got to make it so my information is random and that it's bias free. Now, with all that out of the way, the purpose of this video is we're going to talk about determining the probability of samples. And so what we're going for here is, once we get a sample, the same thing that we were talking about with our friend single value X. Now we're no longer talking about a single value. We're talking about the probability of a sample, specifically a sample mean. So, with all that in mind, let's go to the magic whiteboard. When we're talking about sampling, specifically sample means, we're talking about the likelihood that a sample mean is occurring. So, first get reacquainted with some terms. We have our friend mu, which represents a population. We have our friend sigma, go phi sig, that represents the standard deviation, the correspondent of that population mean. And these here in blue, I'm just going to have blue as be my population color, and then my X bar is my sample mean. And of course, that is simply an average of values in the sample. Now, to determine that, I'm going to have a sample size called little n. And little n is simply the amount of measurements I take within a sample. So let's suppose that I work for this company, ICE, and my job is to make sure that the weights of these come out within specifications that my company has set out. And that would be referred to as the population mean and standard deviation. So in other words, the powers that be at ICE have said, hey, we're going to produce, all of our bottles are going to have an average of 500 milliliters and a standard deviation of 0.2. And so my job is to check to make sure we're in specification. Now, here's the tricky part. If I'm going to sit around all day at the production plant and count and weigh every bottle that comes off the line, that's really just not even possible, because then no bottles would go out the door, we wouldn't sell anything. So I can't do that. What I have to do is take a sample. Well, let's say that I take 5 bottles off the shelf and I weigh those bottles. That would be a sample size of 5. And let's say that my weights are 500 on the nose, another one is 500.1, another is 499. So those are my sample weights. I have 5 of them, 1, 2, 3, 4, 5, because my sample size is 5. And I chose to weigh 5, and I'm going off a sample of 5. So to get that X bar, that sample average, I'm going to add these up and divide by 5. So to get that value, I could go to Excel, but every time I do one of these videos and I go to Excel, all of a sudden I kind of sound like human melatonin. So I'm not going to do that just yet. Instead, I'm going to confer with my friend, the chicken. So if I were to take those numbers there, chicken, and add them up and get the average, what would it be? Chicken says 499.63, so we're going to go with that. So there we go. We've got our sample mean, X bar 499.63, sample size of 5. So what? Well, we want to know what the likelihood of a sample average is of 499.63, what the likelihood of that is to occur. And so like we've done before, we could say or less or more. For now, let's go with or less. So just like before, we want to do 2 things. We want to convert that to a z-score to see how many standard deviations it is away from the mean. And we're going to take that z-score and we're going to go to our friendly neighborhood z table to determine the likelihood. We'll start out with what is the likelihood of a sample average being 499.63 or less. So we are going to begin with z-score. And so we're going to take that, instead of single x this time, we're going to take x bar, 499.63 minus our mean, Now this time, remember here for our formula for the z-score of x bar, we're going to take our standard deviation of our population, which is 0.25, and we're going to divide it, here's where the difference is, by the square root of 5. Now you might remember before, when we're determining the probability of a single value x, our formula looks similar but a little bit different. Here's what I mean. Back with single value x, this is the single value, x, instead of x bar. No big deal. But down here, we don't have the square root of n. We just have the standard deviation. And mathematically, we can remember that makes sense because if we had a sample size of 1, which isn't really a sample size, then the square root of 1 would be 1, and this wouldn't make a difference, and it'd be the same thing. So, the formulas are not that different. Here's what's potentially going to trip you up. It has a common tendency, or has a tendency to trip people up. If we don't watch out, we're going to gum up something down here in our calculations. One way we can be bulletproof on this is to do this in Excel, but I'm not going to do that right now. I'm going to show that in a later video. For now, I'm going to stay on track, and what we want to do is we want to take that square root first, and then we want to take, see, I'll just annotate this, how we want to do this in our calculator or consulting the chicken. We want to get that square root of 5 first, and then we want to get this whole thing first, 0.25 divided by the square root of 5. At the same time, we'll just call that 2 alpha. We want to get this up top, the numerator, and then we want to get the numerator divided by the denominator last. So, to save some time, I'm just going to consult the chicken. Hey chicken, what do you think about these calculations? Okay, chicken thinks that this is equal to negative 3.31 for z-score. And we round it up to get that. So, let's go to our z-table. All right, from looking right here on the z-table, we know that we're going to go down to negative 3.31. And we're going to go over to that 1 column here. So our value is going to be 0.0005. So again, with single values, we have single value x minus mu over the standard deviation. With the single value, or excuse me, with the probability of the sample mean, I'm just going to put the changes in red. But really, that's it. Those are the changes. So when we're talking about less than, when we're talking about the probability of a sample mean more than, when we're talking about the probability of a sample mean within an interval or a range, or if we have a probability and we want to determine the sample mean. So really, all of these, assuming that we know the probability mean, or excuse me. So we know how to do these with single value x. The procedure for doing them with a sample mean is no different. We just have a different formula involved. However, assuming that we know the population mean and standard deviation. If we do know the population mean and standard deviation, then we would use this formula right here. If we don't, then you need to check out my next video.